Homework 1.7, Inequalities, Video 4. Homework due Saturday, May 16th, 2020 at 11:59 p.m. Linear Inequalities, Part 3. It's like it never wants to end. So for this third and final part of linear inequalities, we still have more types of inequalities. You can't see off the screen, but I've got my table of contents over there. After this, we have 2, maybe 3 more videos. But I digress. I want to show you one more variation of linear inequalities, and what I'm about to show you can transfer over to different types of inequalities. Solve this mess. Now you might think that the issue with this is the size of the problem, but the truth is it's not. The size of this problem is irrelevant as long as you have a general plan of attack. In this case, on the left side, we have 8 times open parentheses 6x minus 3 close parentheses minus 12x. There's a lot we can do on the left side by itself, such as distribute and combine like terms. On the right side of the less than sign, we have 6 times open parentheses 1 plus 6x close parentheses minus 23. And again, on the right side by itself, we have a distributive property we can pull off along with some like terms to combine. So what's the issue here besides the size of the problem? Well, I invite you to pause the video and try to solve this one. And if you solve it correctly, you should run into a problem. It's a little stealthy and maybe you can't see it right up front, but as you get into it, you'll discover it. In the meanwhile, I'm going to go ahead and start solving it. Whenever you have a chunky equation or inequality, either the left side, the right side, or both sides, a good strategy is to clean up each side individually before you start looking at the problem as a whole. So let's clean up the left side of this inequality first. First by distributing the 8 across the parentheses to get 48x minus 24. Now we still have a minus 12x, so let's go ahead and write that down. And now that we've distributed, we've unearthed some like terms. We have a 48x minus 12x, which is 36x. And we still have the minus 24. Both of these are on the left side of the less than sign. Now let's clean up the right side. Again, first by distributing to get 6 plus 36x, and we still have the minus 23. And if we combine the like terms, the 6 and the negative 23, we get 36x minus 17. 6 and negative 23 is negative 17. Okay, so we've been in this situation before. X is on both sides. But do you see the problem that's about to happen? When you're solving an equation or an inequality and you have the same term on opposite sides, you get rid of one of them. So what do you want to get rid of? The 36x or the 36x? That's the problem. They match. Regardless of which one I try to get rid of, let's just say you want to get rid of the one on the right by subtracting 36x, you're accidentally going to get rid of both of them. The 36x's cancel on the left, leaving negative 24, less than the 36x's cancel on the right, leaving a negative 17. And now we're kind of in a quandary because our goal is to get the x by itself. But in an effort to do that, we accidentally took out all the x's. Did we do something wrong? No. This problem was destined to do that. But the question now is, what do we do now? Well, first let's look at the sentence or the statement that remains at the end. Negative 24 is less than negative 17. Is that true or false? Negative 24 is less than negative 17. Now, when it comes to comparing negative numbers, some people have a little difficulty determining if it's true or false. So a visual might help. On a number line, which number would be further to the left, negative 24 or negative 17? The answer, negative 24. Remember, to get to negative numbers, you start at 0 and go to the left, so you would get to negative 17 before you get to negative 24. So the statement we're checking the truth value of, negative 24 is less than negative 17, is equivalent to negative 24 is to the left of negative 17, which it is. So this statement is true. Negative 24 is less than negative 17. But what does that mean in the context of solving this inequality? We're trying to figure out what x equals, and all we're saying is that this statement is true. Well, here's what it means. This bottom statement is true, regardless of the value of x. In other words, the truth value of this inequality is independent of the value of x. No matter what x is, this will always be true. Well, everything I've just said can go all the way back up to the beginning. This statement is true, regardless of what x is. The truth value of this is independent of any x value. Any x value will make it true. So what's the solution? Well, before I give you the solution, let me tell you, I guess, the moral of this story. If you run out of variables, which I just did, I ran out of x's, and the remaining sentence is true. And the remaining sentence, and it is a sentence, it has a verb and a subject and all those good things that sentences have. And the remaining sentence is true. Emphasis on the word true. Then, that means that the original inequality is always true. X can be anything you want it to be. So the solution is all real numbers. Any number you want will make it true. Now in the homework, when this happens, they will ask you for the interval notation for all real numbers. Well, picture this. Well, we don't have to picture it, let's draw it. If you want an interval, you have to describe what you shade on a number line. Well, if the solution is all real numbers, that means I shade the whole number line. So from left to right, what's shaded in? From negative infinity to positive infinity. This is the interval notation for all real numbers. So, the moral of this problem is, well, it's right here. If you run out of variables and the remaining sentence is true, then the solution is all real numbers or negative infinity to infinity. But this raises a natural question. This is what you do when you run out of variables and the remaining sentence is true. So you know what the natural question is. What happens if the remaining sentence is false? Well, we're not going to do a whole other problem. We're just going to modify this one and then I'll tell you the conclusion. If I were to change it from less than to greater than, nothing else would have changed. Except at the very end, we would have gotten a statement that's false. So what does that imply about the solutions to this inequality? Well, let's think about this one and transfer it back up top. This statement is always false. It does not matter what x is. No value of x will make this true, so no value of x is a solution. This inequality is false, no matter what x is. No value of x will make it true. So it's always false, and so no value of x is a solution. So does anybody know what the corresponding sentence is when you run out of variables and the remaining sentence is false? Let's write it over here. If you run out of variables, comma, and the remaining sentence is false, and the remaining sentence is false, then there is no solution. There is no solution. There's a symbol for no solution. You may have seen it before. It looks like a circle with a slash through it. It's actually a Greek letter, but in set theory, it's the symbol for the empty set, the set that contains nothing in it. So if I were to open up a box and said, give me all my answers, it would be empty because it's the empty set. So in the homework, when you run across these and it's towards the end of that batch of 7, be prepared for, oops, I ran out of letters and it's true, so everything works. Or I ran out of letters and it's false, so nothing works. In the remaining videos of the series, we'll take a look at some inequalities that are not linear.